Right, this is matter and radiation question 4. Oops, get the pen on. Let's see what's going on. An atom of argon 37, 18 argon, is ionized by the removal of 2 orbiting electrons. Part A, how many protons and neutrons are there in this ion? Well, the proton number is the one at the bottom, just down here, so there's going to be 18 protons. It's the atomic number for the chemists. To work out the number of neutrons, you take 37 minus 18, which is going to give me 19 neutrons. The fact that it's been ionized has nothing to do with the nucleus, so it's just orbiting electrons, so presumably that will come up later. Part B, what is the charge in coulombs of this ion? Well, if we've lost 2 electrons, that means that we'll have a +2 charge. So we've got +2, an extra 2 protons effectively, which are going to give the ion this charge. 1 proton has a charge of 1.6 times 10 to the minus 19, because the charge on an electron is minus 1.6 times 10 to the power minus 19 coulombs. So it's just 2 times this number here. 2 times 1.6 times 10 raised to the power minus 19 gives me 3.2 times 10 to the power minus 19 coulombs. I would actually put a plus sign in there because we've lost these 2 electrons. We've got a positive charge, and I think it's worth stating that, even though it reads positive anyway. It's definitely something worth doing. Okay, let's rub this out and look at part C. Okay, which constituent particle of this ion has a 0 charge per unit mass ratio? So specific charge per unit mass, is Q over M. Well, all the constituents have some M, so it's looking at this top number here. We're looking for the one which has 0 charge. So that must be the neutron, because 0 divided by anything is obviously 0. Your answer will be the neutron. The neutron doesn't have a specific charge. That's part 1. Part 2, the largest charge per unit mass ratio. So again, it's Q over M, the specific charge, the charge to mass ratio. I'm looking for something with a small mass and charge, a large charge rather, and a small mass. Because if I divide by a small number, I'm going to get a big number. So looking at the proton and the electron has a much smaller mass. It's obviously going to be a bigger specific charge. So we can just put electron. I do think they give you the specific charge of the electron in a data sheet nowadays. Part D. Make some space for this. Right, part D. Calculate the percentage of the total mass of this ion which is accounted for by its mass of its electrons. So what I'm going to have to do is work out the mass of the electrons, and then later on I'm going to have to work out the mass of the entire atom and divide one by the other, which should give me the correct answer. So an electron has a mass of 9.11 times 10 raised to the power minus 31 kilograms. How many electrons have we got? Well, we've got 18 protons. We've ionized this particle, remember, so there's now only 16 of these. So the total electrons is 16 times the mass of the electron, 9.11 times 10, raised to the power minus 31, and that gives us an answer of 1.45 times 10 raised to the power minus 29 kilograms. Okay, well, remember that number. Now we need to work out the mass of the nucleons. I should call it Mn. I'm not sure what they call it. It's been ionized, but that makes no difference. So we've got 37 nucleons. So I'm going to do 37 times the mass of average mass of a proton or a neutron, 1.65 times 10 to the power minus 27, and that will give me 6.105 times 10 to the power minus 26. And to work them out as a percentage, all I need to do is divide, I'll show you on here, I need to divide this number by that number. Really, this bottom number here should include the mass of the electrons as well, because it says the total mass of the iron bolts. This number here is going to be much smaller, so it won't make that much difference. So I'm not going to bother with that. We've got 1.45 times 10 to the power minus 29 divided by 6.105 times 10 raised to the power minus 26. And that gives us a ratio of 2.38 times 10 to the power minus 4, which is approximately 0.24%, which sounds about right. Total mass of the the electrons compared to the total mass of the atom is going to be very small. So 0.24 sounds about right. It's probably why we don't account for it very often. We don't really do much with it. Okay.